Good. There we go. Okay. You guys have seen this diagram before. This is a framework which I've tried to use to understand air-sea coupling in the mesos, in which there's three different ones. One is SST. If the SST is warmer, then you get convection. We heard a little about this morning. Second one is if you have convection, it reduces the heating of the ocean because the clouds block the short wave. But the one I want to talk about today, and the one which this group is most well set up to deal with, is the one where you have an anomalous air-sea flux. Say you have more heating of the ocean, how much does the temperature increase? That's essentially saying how much does SST change in response to air-sea flux changes. That can be expressed as an effective mixing depth, which is not necessarily equal to a mixed layer depth defined in some arbitrary way. The context is we had a very successful, I just watched, had a very successful field year. In 2018, there's another one coming up. Are there ways that what we do in 2019 can address this question more directly? So, first of all, I have to do a mea culpa. Many of you have seen this figure before. This was a figure which is from the Woods Hole mooring as the year-long record. SST is in reddish color here, and the blue is a year-long record run from PWP mixed layer model, which remarkably well tracks the mesos. From which so there's several possibilities as to why this is so good. One is that 1D mixed layer models work really well, and that's what I claimed, because after all, if you get a wonderful result that makes you feel good, you have a tendency to say that that's the answer. The other answer, which is correct, is that there's something wrong with this situation, and you weren't really willing to look at it carefully enough. This is also the difference between a talk you give at a meeting and a published paper. A published paper has to be right, what you say at a meeting just has to sound right. This was all pointed out to me by Jared Buckley, who's going to tell you about this in more detail tomorrow. The short answer is that in this model run, the air-sea fluxes were computed using the model SST, not the real SST, and that nudges SST to air temperature, which is SST, which is why it tracks so well. So this is an artifact of the model. That's not right. Oh, right! Do we get the weight, or what was the reason? What was the reason? Okay. Okay. Well, anyway, there's some reason that I didn't know about, and we demonstrate that I still don't know what I'm talking about. But that's okay. Okay. Never mind. Moving right along. One should be. That's what you told me that before. That's what I did. Oh. And then you made it. There are many ways to screw up, and many of us have done many of those ways. Okay. Good. Moving right along. I want to talk a little bit about data and a little bit about some other work we've been doing. I've been working since 2015 with INCOIS, deploying floats that look like this all over the seas around India. There have been 6 deployments so far with almost 200 days. Here's where they are. One real long one here in 2016. Typical data that you get is depth versus time. That's a couple weeks. And this in particular is equivalent of a Richardson number. Any color that's greenish is unstable. This was a response to a modest Cyclone Roanu in 2016, and you can see this very strong deepening associated with Roanu. The other thing which is interesting about this case is it's a pre-monsoon case that looks a whole lot like what happened in 2018 at the onset, and it just shows that there's a whole lot of deepening, and you can diagnose it with this. So, and this is an ongoing thing. Like last year, we had 2 deployments. And I expect it to continue, and it's been really, really good collaboration, and these guys have done a super job in making this work. I didn't go on any of these cruises. That's what the float looks like. It's a modified float with a little extra buoyancy. We have an ADCP. We also have some optics which never been used, and 2 CTs. But the real interesting thing is the combination of the ADCP, which gives us shear, and the 2 CTDs, which give us stratification. I ran some modeling of this, and this one I actually checked out. I'm pretty sure it's right. I don't think I screwed this up. Here's a story. The story again is a week and a half. This is temperature before the storm comes. There's diurnal warming. The storm comes here, and it deepens down to about 50 meters or so, and then it re-stratifies. And this is due to shear mixing. You can see that this is a very nice diagnostic. Richardson number-like quantity, which shows how deep it is. The deeping here goes to about 55 meters. The interesting thing is there's about 2 degrees of cooling, and similar cooling of that magnitude happens over the whole Bay of Bengal in response to this storm. The short version of that is basically in this time of year, it's so primed for being mixed, any strong wind will mix to many tens of meters and erase the thermal stratification from the months of solar heating that happened before that. This is submitted to Jake. You have a there's been no wind for like 3 months or 2 months. There's all this very thin hot layer. All you need is a little bit of wind and it erases it. It doesn't, in other words, if you want to know how much it's going to cool, it's how much temperature the gradient it has in the upper tens of meters, and you'll just mix it away no matter what you do. In the place where the winds are strong at the center of the storm, there's almost as much cooling as there is off in the periphery. Because once you get the cool down here, there's not much temperature gradient left. So it doesn't matter how much you entrain. You get about the same cooling, which is an example of where the details of the mixed layer model don't matter much at all in this particular case. Here's a model run of the same thing for the PWP model. You can see that it mixes to about the right depth, and the restratification is completely wrong. That part is completely wrong, but the amount of mixing is about right. You can look at that. This is what I get, more or less what I just said. You can look at that also in sort of a sensitivity study. If you look at density, black line is the model. You get about the right amount of density mixing because this is a density model. You get not quite the right temperature and completely wrong in salinity. You get about the right mixed layer depth and about the right mixing depth, and except right here where the fluxes say it rained, but maybe it didn't really rain. So the important thing about this is, one of the important things, is that you get density right and you get T and S wrong. And the reason for that is because this is a horrible place in terms of fine temperature, fine structure. This is the TS diagram. Basically, there's 2 different water masses with a significant salinity change and a little bit of temperature change. And the front crosses that front right during the middle of the storm, being blown by the storm winds. And the important point is that this sort of situation, not quite as extreme of this, is generic in the Bay of Bengal. It's always something like that. And that brings me to the last slide, which is supposed to be controversial. And it's my opinion that because of that, because the Bay of Bengal has always complex TS structures, lots of small lateral scales, I think it's very unlikely that making lots of detailed studies like this is going to make very much progress. It's just not the right place to do this sort of work, nor do I see any physical reason why mixed layer models should be much different in the Bay of Bengal than any place else in the world. And so I just don't think this is a particularly constructive goal. It's useful to document how things are working, but I don't think this is the place to do a mixed layer study. The other reason is, if you look at what's state of the art in doing mixed layer studies, it involves making detailed turbulence measurements and making detailed surface wave measurements, and we're not doing that, nor are the right people to do that stuff in this group. So this is supposed to be controversial, okay? So just let me finish, and then you can shoot at me, and then since I'm just here to give advice, you could do whatever you damn please after that, So I'm just here giving advice. You don't have to believe it. As an alternative, I want to go back to this diagram that I had at the beginning, which is looked at from a coupled air-sea perspective. One of the things we want to do is say, given so much air-sea flux, how much SST is there change? That's not a point measurement. That's an area average measurement. So we don't really want to know that at a single point, which is where the advective and fine scale problems are the worst. You want to know it over some spatial area that's some sort of size. And we've been saying that for a while. And the question is, well, what size should you have? And I was attempting to sleep with an overly hard mattress last night, and it occurred to me that the right is still a lovely place, but the mattresses are really hard for my...
I now need clarification on every statement.
I will stand by the fact that I think the mattress is too hard for my taste, but my shoulder is slowly getting used to it. Okay. We have some agreement here, okay, but anyway, never mind. So the question is, what would be a good target scale? If you want to do some spatial average, you have to pick a scale. I think we've been hung up on that for a while. And it suddenly occurred to me that a central measurement for this problem are the microwave SST measurements, because SST is a really central thing for this problem on both sides of the interface. It's cloudy, so you can't use IR. And so the real measurement you need to do SST is microwave SST, and that occurs on a 25-kilometer pixel. So that seems, and it seems like about the right scale. It's bigger than a cloud, smaller than the Bay of Bengal, bigger than a bread box. And there also may be some subtle issues with this from a CalVal point of view. First of all, it looks through the clouds, but maybe these clouds are a little different. Maybe what works in one place doesn't work in other places. And it's corrected for diurnal warming, but we have, because of the salinity stratification, we have rather special diurnal warming in the Bay of Bengal. Maybe these corrections aren't right, and the corrections to get to these SST products are converted to temperature at the coldest time of the day, and maybe that's not quite right. So just from a CalVal point of view, there's something interesting. But
they just throw out the daylight.
yeah, but they're still not at the exact coldest time of the day. They Yeah, okay, so anyway, maybe there's not issues, but you might want to think about it. It's really important that we get this right. So let me go back to the question. The question is, how does average SST change in response to air-sea fluxes? Another way of saying that is, what is the effective average mixed layer depth, not the mixing depth, not the mixed layer depth. And so in the presence of lateral variability, fronts, filaments, and all sorts of stuff, that you have to figure out how you average heat at a bunch of places to get the average. That's an interesting problem that's unique to this thing. It doesn't have to do with boundary layer physics. It has to do with a whole range of physics. In particular, it has to do with all sorts of physics that we've been paying a lot of attention to, namely fronts, lateral mixing, cold pools, rains, clouds. These are all things that change the lateral distribution of SST. How do you average over those to get an average product? What actually are those scales? How do you average them? Is there some interesting physics associated with it? Probably. And can you understand and model these within the context of this variability and the issue about how you go from fluxes to SST? And so that's a suggestion of how you might design a sampling scheme, which got to have some spatial distribution. You've got to worry about not aliasing yourselves on a diurnal cycle and all that sort of thing. So there's what I had to say.
We have time for a couple of questions.
So you want you thinking of some? Oh yeah. So you have the average mixed layer depth. You want to average over all of the filaments and fronts within the 25-kilometer box.
Or something like, yes, because that's what the atmosphere does.
Right, and that's sort of the target of the next generation of model resolution, and you can observe that scale.
You could make it 100 kilometers.
So you're going to have a lot of weird nonlinear interactions in your spatial.
Precisely, and that's what's interesting about the problem.
And is that a constructive way of thinking about it that will work for modeling? That's a question.
You had a question?
The mixing depth is the ratio of the flux to the change in SST. In other words, dSST dt is flux divided by mixing depth. Both quantities averaged over the scale you're talking about.
And does it make sense to do that at points? Because it's going to be a lot of variability across.
That's exactly the point. There is lots of
That is the
variability.
point.
You must do it at lots of points and figure out how to do that average. That's exactly the issue that's interesting.
Given the very shallow layer of fresh water, a lot of the sunlight, about 30% of the incident sunlight escapes below it. So you have to account for that if you're thinking in terms of a depth.
Two things. One is that's certainly true. That's certainly true in once the fresh water arrives. For at least half the monsoon, it hasn't arrived, and we're talking about mixed layers that are a lot deeper. But you're still right. And yes, that's also part of the issue. But just because the heat goes below the mixed layer depth now doesn't mean that that water didn't come to the surface at some other place or other time. That's the really complicated part of this, which might or might not be important. I don't know. Yeah, I'm out of here.
Speaker again.